Hello everybody, my name is Said Zarinmer and in this tutorial we are going to continue our discussion about activities in mandatory occupancy simulation models. If you remember from previous tutorials, we discussed that what is an activity model, and then we also discussed some of the basics of the potential field, which is the navigation system of the activity model. We used a simple example and the office example as well. We are going to continue our discussion with this simple example. If you remember, we discussed that the um, we try to demystify the idea of shortest paths that you can see in here. The shortest paths are not useful because they will collide with the barriers, and there is the desire to minimize the path lengths is not the only desire that should be considered in path planning. There are other desires, for instance, being away from the barriers while walking is another desire. So all of the environmental factors can be important in path plannings, and the uh, in total, what we want to achieve is to offer a path planning system that maximizes the comfort or minimizes the discomfort instead of just minimizing the length of the path. So these are the shortest passes. You can see all of them will touch the edges of the barriers, and if we consider the desire to be away from the barriers, which by the way can be visualized like this. So this is the edges of the walkable field, and I'm just going to show that. Then this is the cost of being close to the barriers, and then if I go ahead and select a different brush for the path, let's say mm, this color seems good, and capture the paths after accounting for the desire to be away from the barriers, you can see that they will look very different. And they seem to be like the choices that every one of us will make. And in this tutorial specifically, I would like to focus on the cost parameters. So if you remember from previous tutorials, we have introduced parameters in OSM environment, and then we created the cost functions for layers of data that are parametrized. So let's take a look at the data that we have on the background, which is the distance from edges of the walkable field. And then if you go to this control panel, you have the option of visualizing the cost function associated to that, and this cost function is something like this, which means that when you get closer to the barrier, so for instance in here, then you will be feeling more uncomfortable, and then you want to uh, get away from the barriers, but at certain range it doesn't matter at all, so it will become zero, the cost associated with that. And this built-in repulsion case is actually uh, based on two parameters. One of them is barrier repulsion range, which is a variable between 1 and 5, and the default value 3, and the maximum repulsion range, which is a variable between 1 and 20, and the maximum and the default value of 10. And then we have also another variable in here, which is uh, the effect of the distance itself. That is also parameterized, and you can change the parameters in here. So I'm going to clear the screen and then create a completely new layer of data, and um, create a new potential field for the sake of demonstration with parameterized costs. And let's go ahead and clear the screen from these paths. So in order to create a path, I'm going to create a layer of data. I'm going to um, um, use the polygon method, and I'm going to call this layer of data repulsion and attraction. And soon you will realize why this name is going to be used. So the default value for the entire floor is 0. I'm going to associate some cost to this area with the value of 10. So this is our value of 10 area. I want it to be symmetric, so I will assign the value of 9 minus 10, and then the cost of minus 10, which means is actually a way of saying that this is more desirable. So the cost of minus 10 means that the attraction of 10, and the layer of data is created in order to get more consistent gradients. I would rather to, and I would suggest you smoothing the data. You don't have to increase the range of smoothing the data. So this is our repulsion and attraction. I would call that S5 in order to give it a meaningful name. And let's visualize our data. The data that we have created in 2D will look like this. And so this is the area which is undesirable, and this is the area which is desirable for us. It can be anything. It can be like based on temperature, daylighting, whatever value that you can capture from other simulations. And then I am going to associate a cost function to that. So let's go to the data control panel and write a formula for that. So the initial value, the initial cost value is the value of the data itself, but I want to parameterize that. And I would create a new parameter. I would call it cost parameter, and with the minimum value of 0 and the maximum value of 10 and the default value of 1, I will create this parameter and add it to the parameters that we already have, and then I will insert it in here. And this is our cost function, which is, this is actually going to be our slope. This is a very simple function, and we have a cost function and we want to include it in the static cost. So there would be in overall two different layers of data that are included, and both of them are parameterized. So this layer is included and this layer is also included. And then I would like to create a new activity, activity 2, and then let's say that the center of the doorway is the destination. I'm not very much concerned with the direction of the agent because we were discussing about the activity and potential field itself. And let's create our activity. All right, before I capture paths, I would like to go to the 3D environment and visualize the way that this data looks like. So this is our data in 3D. This is activity 2. All right, so you can see that we have a nearly flat area and a high slope in this area. Maybe it would be better if I put some contours on the top of this geometry. So you can see that we have a nearly flat area in here, whereas we have a high slope in here, and the rest of the floor in the around the center of the activity area seems pretty symmetrical, but these effects will be influencing everything after them. So uh, with that said, let's try to capture the paths, and I am going to the path planning and draw paths. So this is one path, this is another path. You see that the path that we have extracted, this is the gradient path, of course, is actually avoiding this area, but at certain point it says that, okay, you know, the path length will be too long if I try to make a long detour and it enters this area. But when it enters this area, it enters it in a way that it wants to minimize its presence in this path. And And for these areas, it's not going to be very different, but take a look at this one. This is exactly the opposite. This is minus 10 and this is 10. And then for minus 10, it's an attraction, and then the agent, instead of going directly, it will actually make a longer detour in order to maximize its presence in the attraction environment. And uh, and uh, for these areas, it's going to be symmetrical as the 3D visualization suggested. All right, so we have parameterized our cost function. And now what will happen if I go ahead and just update the parameter? So this is our cost parameter, and then let's make it much smaller, right? Let's, I'm not sure. Okay, let's say zero point 0.2 and update the parameter. In order to uh, update the potential field, you have to go in here, select this guy, and then update it from here. I mean, we haven't updated activity 1, it's activity 2 which is updated. And then let's go and capture the new paths. I would expect to see something which is different. And let's select a different brush. And then this time I'm going to dealing with a lot of colors. Okay, black. Black is a good choice. And so it is still is trying to get away from here, but now this is going to be different. So because this area is not as unpleasant as it was before, the agent would rather to take this path which is traveling inside that. But you can see that there is an effect inside this area, and the agent tries to minimize its presence still, but in a lower way. And these areas didn't change so much, these paths. How about this guy? Oh, it's actually different from the previous one. It's like you can say that I still like this area, but I don't like it as much as I liked it before. So these passes are different, but it's still the attraction exists. So the takeaway from this tutorial is that we can control the path planning system by the system of parameters that we have encoded in embedded in the cost functions. So if we change the cost functions associated to the data, we will get different paths. And these cost functions in total, they will determine the way that we would be walking in the environment, and they might be different from one agent to another agent. So let me clear this area, clear everything from this screen. And I would like to elaborate on the effect of potential fields on our behavior. So this is the potential field. Okay, let me visualize the potential field in 2D. So this is activity 2 with 40 color steps is fine. And you can see that we got a lot of different colors in here, and these colors are different. So for instance, in here you can see a shape like this, and you can go to the dynamic gradient visualization. So these are the forces that are pushing the agent towards the passes. So this force is actually taking the agent to the destination, and then this force will change. This force is actually, you see, this force at this point is taking the agent to this desired area, and then I would try to navigate with the direction of the force and take it to here. So these forces that are filling the floor are actually is actually the derivative of the potential field, and the potential field is a bunch of numbers. It's another layer of data. And well, I mean, this might be a good location, good point at this tutorial to go back and talk about the social force model concept. This concept of social force model was introduced in 1951, and later it had been picked up with the scholars in pedestrian dynamics. One of the most famous ones is Helbing, who introduced the idea in a paper in Nature. And uh, the idea says that the social fields can be translated into forces, and those forces can determine the behavior of the agents, of people in the environment. And this is an example. So for instance, we have an agent who wants to travel from point A to point B. There is a destination seeking force, and there is a barrier, and there is a repulsion force from the barrier. So there is attraction and repulsion at the same time. And this is not technically the way that the forces are calculated, and I don't want to make it very complicated for this tutorial. But if you have a mechanism of, let's say, simply adding all of these forces with each other, then you will get a potential field. And then that potential field, you will get a social force model. And that social force model can account for environmental qualities as well. So in this shape on the right, you will see that this path has changed in order to make the overall satisfaction better from the environmental qualities that you can see on the background. Darker colors are actually not desirable. Well, actually, I've developed this one in years ago in for a crowd simulation paper in Rhino and Grasshopper. So these are a bunch of agents that are not really comfortable because their personal territories are actually violated, and then when they get the chance they want to relax, and when they are relaxing they are pushing each other away in order to make a space and retain their personal territories. So in this tutorial we discussed that we can integrate the desire or undesirability, and overall we would call that cost functions of different layers in the path planning system in much the same way that we can account uh, for the length of the path. And this is very important because it makes path planning unique to the people's personal preferences, and it will make them more reasonable because we would be offering a system for path planning which makes the paths more comfortable as opposed to shortest. In the next tutorial, I would be giving you some more examples of which I believe will be useful for creating activities and potential fields. And thank you very much for um, watching this tutorial. I hope I see you in the next tutorial as well.